Excellent. Thank you, everyone, for coming this afternoon. Really appreciate it. Thank you, Alexa, for that nice joke and intro. I'm going to just jump right into it. We have a relatively short period of time here, so I will just start off by asking who here in the audience is using Hadoop or Spark or any of those ecosystem tools today? Just a quick show of hands. Okay, only a few people. How many people are running those workloads on AWS today? All right. And last, is anyone using EMR to do that? Okay, so then I will spend just a couple minutes talking about what EMR is for anyone that doesn't know. So EMR is a managed service that AWS offers to help you run sort of all of those Hadoop ecosystem tools, the Sparks, the Hives, the Splunks, Spark, Hive, Flink, and other tools in a completely managed way. So if you're running these on-prem today, you probably have a whole bunch of IT administrators that are doing things like making sure your HDFS is up to date and running, making sure that the cluster is communicating properly. EMR allows you to do that as a service, and it allows you to do that also in a pay-as-you-go model. So you're effectively only paying on a per-second basis for the nodes that you need to run your workload at the time that you need to run it. Aside from that, it has a number of different security features, which I'll get into in a little bit more detail. And although you can select just a couple checkboxes to choose which of those tools you want to run today, you can customize those in any way that you want. So we have a bunch of different mechanisms for you to bootstrap those clusters to install either additional tools that we don't support out of the, I think, 19 that we support today natively, and to customize any of those tools in whatever way that you want. So this is a little bit of a visualization of what EMR stack sort of looks like. Starting with the storage there at the bottom, of course, we run HDFS within these clusters. But the great majority of our customers are actually using S3 as their primary data store. So S3 is a simple storage service. And we interact with that through a connector we call EMRFS. And I won't get into too many of the details here. But really why that's powerful is that when you use something like S3 to abstract your storage layer out, you can have transient and short-running clusters that don't persist on and on because your data is able to be durably stored. Why this is powerful is because from a cost perspective, not having compute run when you don't need it to, while not having to worry about where your data is persistently stored, is really powerful, and I'll cover that in a bit more detail. And then in a bit above that, you have your resource management components, your Yarn, your Hbase, and Presto, and then any of the open source tooling that you may want to use on top of Yarn, things like Flink and Spark streaming, et cetera. Adjacent to that, through just a checkbox as part of the managed service, you can also provision things like Hue or Zeppelin notebooks to use. Again, you don't have to be an expert in running these. You can just essentially select a checkbox to allow your developers to build upon that. And on the other side, there's connectors to a number of AWS services. So S3, obviously, which I mentioned, but it has native connectors to connect to things like Elasticsearch, to Redshift clusters, to MySQL and RDS, for example. But I want to also highlight one other service within the AWS environment that's really complementary for these Hadoop workloads, which is Glue. If you're not familiar with Glue, there's a couple primary components. One of them is actually an ETL component, so it's an ETL tool that allows you to drive those types of workloads. But one of the other functionalities within it is actually what we call the Glue data catalog. What this is really a Hive metastore that can do things like auto-generate the schema and partitions of your data that's stored in S3, so your external tables that you have in S3. Manage essentially the updates as you add new data into that. It can modify the schema as new data comes in. And it's really powerful because you can use it with a whole bunch of other services. So you can use it with Athena. If you're not familiar with that, it's basically serverless SQL execution against data stored directly in S3. You can use it with things like Redshift Spectrum. But you can also use it directly with Spark, Hive, and Presto so that they understand and can use that as a metastore to understand where the external data is stored. This is also really powerful since you don't have to persist your metastore outside of a Hadoop or within a Hadoop cluster. And so this, again, helps you create and use those transient clusters instead of having to have long-running and potentially costly Hadoop clusters. And lastly, before I move on, this is another feature. Customers have been asking us They're telling us we want to run Hbase, but we don't want to run these really, really costly and large HDFS implementations. And so we've come up with a solution to essentially abstract out the Hbase root file system and store your H files in S3 directly. And so you can run a much, much smaller cluster for your Hbase implementation and access the data directly within S3 inside of that. One of the other benefits of doing it this way is it allows you to have a separate Hbase read replica that can read that same data in S3, completely separate from your primary Hbase implementation. And this might be useful just in and of itself, but it's also really nice in the event that your primary Hbase cluster has an issue. Really good to have a backup there that you're able to just access directly immediately. So this is a lot of data crammed into a really short session, so I'm just going to fly through it and talk about some ways to lower your costs in EMR. And one of them that I've been mentioning a few times is the concept of transient clusters versus long-running clusters. Today, if you're working in a Hadoop environment, you probably have scaled up this environment to be as big as you need for all of your jobs to execute across it, no matter what size they are, whatever resource constraints that they have. Some of them might need a lot of memory, some might need a lot of CPU. When you only have to pay on a per-second basis, and it's really able to be configured ad hoc through some checkboxes, it becomes a lot more compelling to isolate your different workloads and optimize them based on the resource constraints they need. So just to throw up some examples here on the screen, you might have a nightly batch job that needs to process. It might be really CPU intensive. Similarly, you might have an analytics job that runs a couple times during the day, but otherwise, these workloads are probably not running. And so if you don't need to be running them, you don't need a long-running cluster in order to run those. On the flip side, you might actually still do something like Spark streaming, and so you have real-time streaming data. That probably needs to be online all the time so that you can stream that data into that service all the time. But it might be memory intensive, and so you might have requirements for that workload to be on more memory-optimized type of instances. And so when you think of ways to start splitting up your actual workloads, instead of thinking about how you can manage one large cluster to run all of them, there's some pretty compelling ways that you can save costs by splitting them out that way and run only what you need when you need it. Now, furthering this concept, when you start splitting out your workloads, if you're not familiar, there's the concept of EC2 spot instances. What this is very simply a mechanism by which you can use unallocated resources in the AWS environment, so instances that are not currently being used, excess capacity, but only pay 60, 70, to 80% off of the on-demand price. So because we have excess capacity, you may use it for quite a bit cheaper than the on-demand price. So that in and of itself, especially for transient jobs or workloads that can be restarted or pick up from where they left off, really, really powerful from a cost perspective as well. And EMR took this one step further and implemented a feature called instance fleets. Very simply, what this means is that you can identify up to 5 different instance types for your workload. You put a particular weight on them. So in this scenario up here on the screen, there's 4 different instance types, and you've given a unit count for each one of those instances. So that's basically just roughly a weighting about how useful those instances are for your workload. And then you say, EMR, I need X number of units, 240 units to complete this workload. I don't care. EMR, you pick which availability zone has the capacity within Spot to do this in, pick which subnet to run it in, because I want to get as low of a cost as I can, and I don't care which instance type as long as it's one of these 5. And then you can also say, after a certain period of time, if I can't get the Spot instances, just fill up whatever is left over to make sure that this workload completes with on-demand. So you can kind of see how that can be really compelling from a cost perspective. Another mechanism for saving costs on EMR, EMR has the concept of 2 instance types. So there's a core instance type, and those are going to run your HDFS data nodes as well as your Yarn task manager. And then we also have just task nodes, and so those are only running the container execution component of that. And so those are actually a really good candidate for scaling up and down. So if you do have a long-running cluster, but you have maybe spiky workloads, it can be really compelling to use a CloudWatch metric or any sort of metric that you want to pump into that system to scale up and down based on utilization requirements. A couple really common ones that we see are overall cluster memory utilization. That might be one that you want to scale up on. Or even something like yarn containers waiting in a queue to execute. That might be a good indicator that there's jobs waiting to be done, and you can scale up based on that. EMR will scale in at yarn task completion, and it'll selectively remove nodes that don't have any running tasks. Specifically with Spark, we actually identified a couple of optimizations that we could make and contributed those back to the community so that other people can use that in their own environments as opposed to strictly having that within EMR. Let's talk a little bit about cost. I want to talk just finally a little bit about some security components of EMR before we move on. So when we talk about security, I'm going to cover three primary concepts. First is encryption, then I'll talk about authentication, and finally authorization. Within EMR, we support data encryption at rest in S3. This can be either server-side or client-side within the actual EMR cluster itself. You can use the KMS key management service that AWS provides, or you can bring your own keys from a HSM, for example. The way that you describe how this all works is basically a security configuration, which is an abstraction, and then when you launch a cluster, you say, here's the configuration I want for my cluster, launch it with this, and we'll make sure that we deploy it out with the security requirements that you've defined up front. Similarly, in transit, for all the items you can see here on the left-hand side, we support data encryption in transit. That means that basically you identify, here's where my certificates are, and basically point us to how you want to encrypt that data, and we'll help manage that on your behalf, both between the different nodes, generally with data, as well as the HDFS side of things. From an authentication perspective, you can use LDAP for Hive Server 2, Presto Coordinator, SparkDrift Server, Hue Server, and Zeppelin notebooks. You can also just SSH into the cluster using a key pair that you identify when you launch the cluster. Or you can submit using your AWS credentials through the EMR API, the step functions, or the step API, to submit a job directly through there using your AWS credentials if you like. So this is great, but if you operate in a world that has multi-tenancy, you have a multi-tenant cluster, we do also support Kerberos. So what this looks like is essentially that users are able to SSH into this cluster using their federated identities. We set up a KDC on the master node that has a one-way trust with, for example, your Active Directory server, and then people can submit jobs as themselves. And so this is really powerful from an auditing perspective to know what's going on in your cluster, who's doing what, and also to do things like authenticate different services within that same cluster, authenticate different container executions to the file system, et cetera. So if you're running a long-running cluster where multiple users are going to submit jobs, this is really, really powerful. In terms of authorization, it really depends on how you want to choose your authorization layer. A lot of customers are choosing to do this actually at the data layer, so the file storage layer, whether that's S3 or HDFS. And so that's relatively simple. You just restrict which users or groups or roles have access to which subset of files, and then if they execute a job, as long as they can access that data that they're querying, they're perfectly able to do that. Certainly, if you're using any of the SQL-based tooling, they all have their own mechanisms for authorization within those as well. And we actually have a blog post in terms of how you can integrate Apache Ranger to do things like set up granular permissions on even individual columns. So there's a number of different ways to solve this, but here are just a few on screen. And this is my last slide before I hand it over. Historically in AWS, when you spun up a node or a cluster, you could assign a role to it, and that role had certain permissions to access different data sets or other services. But generally speaking, if someone could execute within that environment, they would be able to execute as the root Hadoop context, essentially. So whatever permission that cluster had, that user would have the same permissions when their job executed on. This new concept within EMRFS allows you to have the jobs that individuals are submitting in a Kerberized cluster to execute within a particular role context. So to put that in a simpler terms, if Brad submits a job, you can say, if the user Brad or a group that Brad's a member of submits a job, execute it with the role, such as analytics prod or analytics dev, and so their job will execute in that context and only have the permissions that that role grants them, and other jobs executing in that same cluster can actually have distinct roles. So you can have one shared cluster that can actually execute with different permission sets based on the user that's executing their query.